We had set out into the unknown.
Mission control. We're looking at a red planet.
As long as we looked up at the night sky, that is what we felt.
We now have a successful mission on Mars. It's not just about launching satellites. We need to want to go out there ourselves and see what in the universe is going on.
We were taking a step for humankind.
You ready for this?
Hi, a very good day to everyone. Meeting you with the first episode of VOYAGE in SEDS Space Talks, organized by SEDS Sri Lanka. I'm Rikara from University of Rona. Also, I have one of my friends here today joining with me. So, Nipuni.
Thank you, Chaturika. Let me introduce myself too. I'm Nipuni Vanniyarachi from University of Colombo.
Okay, so let me start this conversation like this, from a quote that just popped up in my mind. Success is no accident. It is hard work, perseverance, learning, studying, sacrifice, and most of all, loving what you do or learning to do. This is a quote quoted by Pelé, a former Brazilian football player. So let me highlight that term perseverance. What are the things that come to your mind, Nipuni?
Yes, Chaturika. What comes to my mind when I hear the word perseverance is keep going despite the difficulties of achieving success. In that context, bringing you this Voyage episode itself is a result of the persevering effort of SEDS Sri Lanka. SEDS Sri Lanka is the Sri Lankan branch of SEDS Globe, and it's the largest gathering of Sri Lankan students and young professional volunteers who love the space and contribute to the space development. This webinar series is conducted by SEDSUOC, which is the SEDS chapter of University of Colombo, and SEDSWAYAMBA, the SEDS chapter in Wayamba University of Sri Lanka, in collaboration with SEDS Sri Lanka. Coming back to the word perseverance, Chaturika, what are the most recent memories that you have with this word?
The most recent memories that I can recall is another giant leap that humankind achieved in reaching the red planet Mars. I think you all have guessed what I am talking about. Yeah, that is the Perseverance Rover that landed on Mars within past few days. So, of course, when we're talking about all the rovers and spacecrafts went out there, they are a signs of hard work and sacrifices. So, when we're specifying the rover Perseverance, today we have one significant person with us to talk about the rover Perseverance and indeed the perseverance behind the mission.
Yeah, that's true. But before introducing the speaker, let's not forget another remarkable person who are doing a tremendous job searching the life from rocky Mars terrains. Being a professor at California Institute of Technology, let me remember Professor Woody Fisher in this voyage. And as the guest speaker for today, we have a student scientist on the science team for the Mars Rover 2020. Also, she is a graduate in geobiology from California Institute of Technology, USA. So please welcome Ms. Hemani Kalucha for today's SEDS Space Talk. Hemani, how are you doing today?
I'm doing so well. Thank you for having me here. I really appreciate it. I'm excited.
Thank you for you too, Hemani, for coming and joining with us. So, of course, we introduced you to our audience, but I'm pretty sure they will love to hear from you about yourself. So here you go.
Definitely. Hi, everyone. So my name's Hemani. I am currently a graduate student, but I did my undergrad in aerospace engineering. And at the university that I went to, we had to do a senior thesis, and mine involved testing SEDSUOC, which is an instrument on the Mars 2020 rover. And I really fell in love with the planetary science side of things, and I wanted to be part of the science investigation of rovers. And I then spent the next year after graduating doing a master's in Toronto, Canada, where I looked at Curiosity rover data and sort of methane measurements and atmospheric measurements to understand why methane on Mars is disappearing so quickly. So I just started my graduate studies, my PhD studies at Caltech in September of 2020, so I'm pretty new here. This is my first outreach talk, so we'll see how this goes. And yeah, I hope you enjoy. I'm ready to get started. That's good.
That sounds amazing. So Hemani, you worked as a student scientist on the Mars rover Perseverance. How was that experience? Let's talk about this masterpiece who's making his voyage in the red planet at the moment.
For sure. I actually have a bunch of slides that talk about it, but I think just for me, I have always wanted to work in space exploration. I've been really excited about NASA since I was 6 years old, and I met this astronaut. And so it's been a dream to be able to be on a mission right out of college. I didn't think that would happen for a long time. And I was really, really excited about the landing and the Mars donuts that we got to eat. Sadly, I couldn't be there for the launch in person, but it's been really cool to be part of the operations. So I'm on the SuperCam instrument team, and SuperCam is, as you'll find out, the one that shoots lasers from far away. And so every week or so, I have a shift where I get to pick where to shoot the lasers, and I feel really excited about that. The first 90 days were also on Mars time, and Mars days are 40 minutes longer than Earth days. So every day I have to sleep 40 minutes later and get up 40 minutes earlier. And so a lot of weeks I'm up at 4 in the morning. So it's been challenging, but a lot of fun.
Yeah, I see. So when talking about the mission, what are your experiences? And you told that you have some presentation slides to share with us. So I'm pretty sure our audience will like to see your experiences and like to share your knowledge with them. If you share your knowledge with them.
Yeah, let me go ahead and share my screen. So can everyone see this?
Yes, we can.
Yeah, we can.
Awesome. So if it's cool with everyone, generally the structure of the talk was I was gonna talk about the rover a bit, and then I'm working on 2 different projects right now. And I was just gonna tell you a bit about my research. Oops, sorry. I'm trying to get rid of these. There we go. And so if you have any questions, feel free to jump in. Otherwise, I'll keep going. So my program is called Planetary Geobiology, and I basically am very, very interested in studying life detection in the solar system. And oh, there we go. And so before I really get started, I just wanted to give everyone a sort of abstract view of how we think of habitability in the solar system. And really, if you had to think of what is the minimum unit of materials and conditions that you needed for us to think that life as we know exists, this is what it would look like. So you need some water, obviously, some rock, some carbon dioxide coming in for those photosynthesis reactions, and these very common elements that we find in all of life, which are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And the most important thing really is that together these work to create an energy source, but that they exist at the same place at the micro scale so that the bacteria can really use all of these together to form. All right, so let's talk about Mars right now. This is just a little bit of a representation of what my operations look like when I'm working. So Mars days are called sols, and this is how the rover feels. So it gets up whenever there's sunrise, and we've sent it a bunch of instructions from Earth for what to do that day. And then the rover carries out these sequences, and it does that by driving around sometimes, by extending its robotic arm that you see there. And occasionally during the day, the satellites that orbit Mars, the rover is going to send back data so that we can come look at it. So that's what it's doing here. And then these satellites actually bounce it back to Earth. And the rover continues with its day, and it goes all the way till nighttime. And usually it takes a lot of naps, but sometimes we make it work at night. So that's what you're seeing here. And then it does it all over again. But really what the human side of the operations team looks like is sort of this. It's sort of us in a room at JPL, and we're crowded around the screen, and the screen is showing us data from that's come back, and we use this to make decisions for the next day. So that part is called downlink. That's the data that we receive, and it comes through the DSN, which is the Deep Space Network. And then a bunch of very talented engineers at JPL that are not me process this data so that the scientists know how to see it and it's easy to use and all of that stuff. And so that's my chair. We look at downlink assessment and we realize, oh, was the rover healthy? Is the rover safe? Was the rover able to do every single thing that we wanted it to do? What failed? What went well? And then we go through a bunch of meetings and we're saying, based on this, what should it do tomorrow? Should it drive somewhere new? Should it take another image? Were we happy with that image? Should it go closer? Should it do spectroscopy? All these things. And the way we do this is there is a software which creates a 3D workspace around the rover, and we can actually see Mars being simulated and the rocks nearby and all of that. And then we get to pick targets. So we're like, the laser should next shoot this rock over here. And then we hand it off and people actually program to do that at a very low level. And that part is called uplink products. And then they're sent to the rover for the next day. And the funnest part of this is that if your target gets selected, you get to name something on Mars, even if it's a little bit rock, you get to name it, which is cool. And right before everything gets uplinked, all the instrument representatives go around, they all say, you know, SuperCam go, MassCam go. And it feels very much like a collective mission, which is nice. And there's also, I just wanted to mention, we're not just coming up with what to do on the fly every day. You know, people have been thinking about this for years. So there's trajectory planning where we first think about, okay, so in this crater, where do we even want to go roughly? And then there's long-term planners who think about this on the level of months. And they're saying, in this 1 kilometer stretch, which rocks are interesting? What do we want to look at? What can we learn if we stop here or here or here? And then the level that I work at is highlighted in red, which is campaign implementation and tactical uplink. And each of these, like very near term, what are the particular activities that we put in the rover schedule that are the most efficient and help us get the most science back in the shortest amount of time? And then after that, the rover planners actually spend a lot of time simulating if the rover can do it safely, if it's going to collide with anything, if it's going to get stuck on a rock, all of these things. So that was sort of an overview of operations. But let's talk about Mars. So that's what it looks like today. Cold, red desert. But we really think that about 3.6 billion years ago, Mars was covered with surface liquid water. And, you know, water, as far as we can tell, is one of the most important things for life to exist. So this makes Mars a really interesting candidate in the solar system. Now, in terms of Earth and Mars, we think that they started similarly with similar conditions, but they really diverge. So what you're looking at here is the evolution of life on Earth. And what you can really see is that the first like clear, easy to see evidence of life comes from fossils. And that really only happened in this yellow arrow over here. And that's only the Cambrian explosion, which is about 540 million years ago. Before that, it's really hard to tell if there's life on Earth or not. And this yellow arrow is when Mars climate becomes different from Earth. So if we want to know if life existed on Mars, we're going to have to get very creative, right? Because there is going to be almost no evidence. And what does that mean? What should we look for if we want to find life on Mars? And on the left, you're going to see a classic fossil. Everyone recognizes that, you know, easy to spot that this is life. But what could we see on Mars is really on the right, and this is called a stromatolite. And we see this on Earth a lot in Australia and a bunch of other places at the age of about 3.6 billion years ago. And what this little rock wavy formation is, it's a bunch of bacteria that have gathered on this surface together, and they emit sort of a sticky liquid, and that's how they sort of grab their food and metals and all their energy, and they keep building up and up and up towards the light. But this is not really easy to recognize because it's, you know, it can be bacteria, it can be natural processes. Everything's tricky when you're 3.6 billion years old, right? What can we do in the meantime, right? So this is it's kind of a summary of what we know about Mars in a weird way. So if you look at the top row, this is what we think happened. There was a magnetic field for a little while up until this purple part. These are ages, billion years ago. So we're talking here like beginning of the solar system. This is the present. There was a magnetic field for a little while. There were some large impacts that we see today. A lot of volcanism occurred really between 4 and 3 billion years ago, and it's really not that much active now. If we're thinking, when was water permanently on the surface? That would be in row D when you see this part over here, and then it becomes really sporadic. So this is when the conditions for life kind of get a bit sketchy, but here we can be more confident that there was some sort of thing going on. Now, this whole thing about Mars sustaining water on the surface is really dependent on it being much warmer. And the way it can be much warmer is that it needs a very thick carbon dioxide atmosphere. And we really don't see that today. The atmosphere is only 6 millibars, whereas we would need something like 1 bar of CO2, right? And so the question is, where did that CO2 go? Because if this sort of cycle that you're seeing on this slide existed on Mars at one point where there was liquid water, you would expect that a lot of CO2 would be stuck in the rocks or something like that. But the huge, big problem with this whole theory is we don't find carbonates on Mars. And that's how the CO2 would be caught up in the rocks in the form of carbonates. So the big question is, where did the carbonates go? You know, how can we be wrong about liquid water, but we can't find carbonates? So one of the theories is it's deep underground. We haven't drilled. We don't know. Another theory is the carbon dioxide escaped. And really the third thing that could have happened is that a lot of volcanism that I just showed you earlier generated sulfuric acid, and the carbonates were dissolved because of that. Here's the other problem with Mars, though. What we do see is tons and tons of sulfates. So these rocks that you're looking at, if you look at the scale, it's 10 centimeters, 20 centimeters. These are whole beds of enriched sulfate, okay? And we also find in the rocks these very extensive networks of calcium sulfate veins. So this is a Mars rock, this is a close-up, this is just a geologic map of it, and everything black that you see here is 98% calcium sulfate. So that's really concentrated. And the one thing that means is how sulfates form on Earth is that they are evaporites in carbonate-poor waters. So everything that we do see on the surface is pointing to the fact that the carbonates are not there. And that sounds pretty grim, but that's where my research starts. And that's where Jezero, which is the landing site of the Mars 2020 rover, gets really interesting because, fun fact about Jezero, it is of course, it's a crater that we think was a lake, but it also has one of the best preserved deltas that we see. And, we have inlet valleys and outlet valleys and pretty convincing signs of water. Even better than that, the orbital data shows that there are carbonates in concentrations like we've never seen on Mars. And so this might be the key to explaining where all those missing carbonates are. And that's why we're very excited about Perseverance exploring this part. So this is what Jezero looks like today. And this is how we're going to explore it. And obviously there's a bunch of instruments here, and I don't have time to go into them, but I can point out, obviously we have a lot of cameras, RGB for the first time on Mars. There's a subsurface radar. There's a weather station for winds and temperature and pressure, and a lot of close-up spectrometers. But the one that I work on is SuperCam. And really, if you see it, it's all the way up here. And this lens that you're seeing is actually a telescope. And it helps to focus the laser so that we can actually point at rocks that are really far away, like 7 meters away. And this is what the instrument looks like up close. And so what it does is it uses the laser to actually vaporize the rock. And then the light that's emitted from this laser-induced breakdown of the rock is something we collect. And the spectra is in the visible and infrared wavelengths. And it tells us a lot of information about the mineralogy and the molecular composition of targets. So these are what the data products look like. This is actually the first target that we've ever had on Mars with SuperCam. It's called Mars. And when we pointed at it, we also get a close-up image from the micro imaging camera that looks like this. And what you're seeing on repeat here is the mic that we have attached to the instrument, and that's what the laser actually sounds like when it's in use. And this on the right side is the spectra that comes back to us, where we can tell all of the elements that are in the rock. So we're really, really excited about where this mission goes, and hopefully get some really cool science out of it. What you're looking at here is a delta remnant, or what is believed to be a delta remnant. And so this part is interesting because it's supposed to have the more fine-grained material left over from the delta. So we're talking about like muds, and muds are well known on Earth to preserve organic signatures really well. So this is one of the first things that we're excited to explore. But I hope you all keep up with the mission. I also, kind of shifting pace to my other project, I spend a lot of time also in the outer solar system looking at carbon dioxide on icy moons, and I'll talk a little bit about that right now. As you saw in that sort of first slide that I presented to you, carbon dioxide is critical to making energy and life happen on Earth. And so the fact that we see it on pretty much many, many different icy moons that I've shown here is really strange, because as you can see from the interior structure of these moons, they're really different. You know, some of them have liquid water near their surface, some of them have double layered ice sheets, some of them are pure rock, and the fact that they share this common signature is really interesting. And as we're following the water in the solar system to look for life, icy moons are a great place because they're one of the few confirmed places where fresh water definitely exists. Whether it can interact with the interior and actually produce reactions that we need is really to be considered, but definitely worth looking at. And these are more pictures of moons that have carbon dioxide. And these are some of the spacecrafts that are able to detect this. So on the left side, they've done Jupiter's moons. In the middle, it's Saturn's moons. Juno has also looked at Jupiter's moons. And they're all about the resolution of like 20 to 30 kilometers. So not super high resolution, but enough to pick up this spectra, which is really interesting. So what you're seeing here is on the left side is the infrared spectrum that we got back from Europa. And you don't have to be a spectrum reading expert. I'm not, for sure. The important part is that we detected this 4.26 micron wavelength, and that really is characteristic of carbon dioxide. But the interesting part is that it's all sort of shifted to the right. So we see it as CO2 ice, but it's really shifted to the right, and it almost looks like CO2 gas. And the fact that that shifting is happening on all of the moons, as you can see, it happens in Callisto on the right too, and in all these other moons, means that there's something weird going on about CO2's behavior, because it doesn't have the right spectra of a solid, and it can't be gaseous if it's detected on the surface. So what's really going on is the question. And if we take the case study of Europa, this is just a surface map of Europa, and this is all the stuff we've detected on the surface so far. So we have some hydrogen peroxide, some regular salt, some magnesium sulfates, and a lot of radiation processing, like in this equation I show up here. And we can use the information about what we detect on the surface to hypothesize about what's going on. So this is a very handmade figure that I just like to use because it helped me understand what could be going on in the surface. And so this yellow part you see up here is Europa's very thin atmosphere. The next blue part is the ice shell. And the ice shell, is hit by radiation. There's ions jumping around. There's all these things. Under the ice shell, we have a 100-kilometer ocean. So almost 1 magnitude above the thickness of the ice shell. And funnily enough, that ocean is in interaction with the silicate core. So all of a sudden, you get processes like all this magma warming up the rocks and creating hydrothermal vents potentially. And those vents may be releasing carbon dioxide that somehow degasses up to the surface with all these circulation flows. So that's one option. But another option is that the surface is being hit by meteorites, which it is, and they have carbonaceous material. And that is sort of getting mixed around in the surface and creating this layer. And what happens with that is that it somehow enters the ocean. And then that could create further reactions that are optimal for life. So it's key to understand, A, where this carbon dioxide is coming from, but B, what are the implications for life depending on that. And one way people have really tried to approach this is by thinking about how it's stored. And so one explanation for this shift has been posed to be a clathrate. The CO2, which is this gas molecule inside here, is stuck in this sort of crystalline structure, and it's a trapped molecule in water ice. And these clathrates can exist in different parts. They can exist in the ice, they can exist just under the ice, they can exist right at the bottom of the ocean where the rocks are. So if we can somehow figure out which of these scenarios is correct, then we can start to understand what processes are going on inside there, and if those processes mean that life could exist. And so that's really where my research comes in, is that right now there's no sort of great match to the spectra from experimental setups. And so what I'm trying to do is really simulate the conditions that exist on an icy moon in lab and try to see what process matches the CO2 spectra that we see. And what you're looking at here on the left is basically a vacuum chamber. And in this, we have a sample holder, and we sort of condense CO2 and water ice together, because that's what we think is the main components of icy moons. And then we have them at the correct temperatures, which is like anywhere between like 70 and 150 Kelvin. And we're trying to see what sort of radiation or other process could really explain what's happening to the CO2. So these are kind of the two projects that I'm looking at, which sort of contextualize how we can approach life in the solar system. And really, that's the end of my talk. Thank you for listening, and I'm happy to answer any questions that you have.
That is an amazing knowledge sharing. We were not just talking about Mars, and we also went to the Europa, which is very exciting. So I think it's time to move to the Q&A session. I request. So I think it's time to move to the Q&A session. I request the audience to raise your hands if you've got any questions, so I can call upon your name. Also, I request you to use your name as the Zoom username when raising your hands. And also to those who are joining us through Facebook Live, you can direct your questions to the comment section so we can ask them for you. Do we see any raised hands? Not yet, I guess, but feel free to raise your hand.
Yeah, there's one.
Okay, let's see who's that. Ramitu Sahalaba. Ramitu, you are free to unmute your mic and ask your question.
Thank you so much, Miss. So Perseverance is powered by a battery that runs on nuclear power. So considering that there are dust storms and it can potentially damage the nuclear battery, what are the measures taken to stop it from any leaks or any sudden power failures? Because we are dealing with such a dangerous power source as a result.
Yeah, that's a good question. That probably the engineers would answer that best for you, but I do know that the RTG is kept encased very well in the heart of the rover. There's also two backup, so there's a backup computer, and if there's ever a sign of power failure, it's often switched to the other computer. In terms of leaks, other than the actual structure of the rover, I don't think I'm aware of any measures, but you have to know that this is not, you know, the size of a nuclear facility, right? We're actually talking about something that only produces about 200 watts. So it's quite a small system, but it's very efficiently designed. Such that, you know, we can do all of this science.
Thank you so much.
Yeah, I think the answer was pretty clear. We have another raised hand. Let's see. Dr. Tharinda Vidanagama. So please go ahead.
Okay, just let me thank you, Hemani, first for joining us, you know, with this new society. I think the students have formed this society, so I think it's a new step in, I guess, the history of Wayamba University, because, you know, this is sort of an unknown area for the university, so I think it's a good step ahead. And thank you for joining us today and giving an insight to what space science really looks like. So, so just want to know, I have, you know, kind of an interest in science as well, but, you know, just YouTube videos. Basically, I'm not doing any stuff. So I've been following this, you know, it's sort of an orthodox, you know, to the new sciences. I think maybe you are familiar with this electrical phenomenon. There's an, you know, sort of an electrical universe people that, you know, they are providing sort of a, you know, kind of a, say, a different theory of how universe is working. Right, so, you know, they were talking about something called Mars blueberries. So are you aware of this Mars blueberry stuff, and they're saying that it's a kind of it's formed due to some electrical phenomena like electrical arcs kind of melting the rock and forming these blueberries or something. So do you think there's an electrical phenomena? Have you detected with the rover some electrical phenomena that as a hands-on experience in your research?
Yeah, so funnily enough, my master's was all about trying to detect this electrical phenomena. And what we thought was happening is that there's a lot of dust storms on Mars, as you know, and they're quite a bit bigger than they are on Earth. On Earth, dust storms are about 10 kilometers tall, whereas on Mars, they're about 100 kilometers. So we thought that this dust sort of would be powerful enough when it rubbed against each other to create electrostatic charging. And because the pressure on Mars is so low, you would actually be able to overcome electric breakdown, and it would create these sparks. And they termed it triboelectric discharge. So I spent a lot of my master's trying to see if Curiosity's or Perseverance's cameras were high resolution enough to detect these and discharges. And the short answer is no, unfortunately. But also they're super unpredictable. We know the crater is massive. Gale is 150 kilometers. Jezero, I think, is on the order of 20, if I'm not mistaken. So, and we have no way of predicting even where these are occurring or when. Our understanding of where dust devils occur right now is pretty preliminary, I would say. So there was a lot of uncertainty in even where to look, what time. I did a lot of analysis on when winds are strongest and if nighttime imaging was a possibility and all of these things. So for the near term with these rovers, it looks like we don't have the ability to detect it, but who knows what happens in the future, so.
Okay, yeah, thank you very much for that. Just another clarification. So I've heard that, there's a big sky in Mars, like Valles Marineris, is it?
Yes. Mm-hmm.
Yeah. Okay. So and that thing is, I guess the mainstream saying that it is, carved by, like the Grand Canyon, so kind of water erosion or something. So, exactly. But I guess in Mars, like, they're asking where the water flowed, like, it's kind of a trench in the middle, but, there's no place that you can see where the water flowed. So right. Is that the answer, like, water erosion or something else?
I think that is the best answer that we have. We actually don't even have good explanations for how the Grand Canyon formed. It's an immense amount of erosion in what we think is a short amount of time. So I think that's our best answer right now. I would also say that the aeolian erosion that Mars had is that we've seen at Gale Crater and at Jezero, there's just large volumes of exhumation, almost 2 kilometers of sediment. And we don't see those wind pressures on Mars right now, but presumably in the past, they were much, much stronger. So I think some combination of water and wind is a good guess.
Okay, thank you for that. Yeah. Okay.
Yeah.
Thank you for the question, Dr. Tarinder. Since we are not getting another one, Ramita Sahalava, you're good to go.
Thank you so much, Miss. With regards to communications within the rover, since we cannot always relay information back and forth from the rover to Earth, so can you describe a bit more on how the specific parts of the rover communicate with each other, as if we find something via SuperCam with regards to the chemical composition of the rocks, it might be useful for MOXIE, and then that would also be useful for Sherlock and Watson. So can you specify a bit on the way the various apparatus in the rover communicate?
Yeah, that's a great question, honestly. So I think there were two parts. One is how do we manage data volume? And you're completely right in that sometimes, it takes a while for the satellites to pass over and the rover has to wait. And so there's actually part of the algorithm is deciding priorities for the data to come down. So when we request an observation, we also say, what is the data downlink priority? And so if we're really waiting on something for the next day, that gets priority 1. But if there's only so much data volume that can come back to us, and there's a huge mosaic that's like 50 megapixels and we know it can't come down immediately, it gets priority 3. And so sometimes things will actually come down a few days later. In terms of instrument data being useful to other instruments, it is really very much a human-run operation in that we get the data and the scientists in the room will actually say, oh, well, we could find this from SuperCam and explore that further with this other instrument. And then in the tactical meetings, we'll sort of coordinate those observations. That is not something that the rover can currently decide.
Thank you so much.
Yeah, of course.
So there's no other raised hands so far. So Chatrika, I think we are good to go with the chat.
Yeah, I think the chat is overloading with questions from our excited audience. So let me present you the very first question, Hemani. What kind of technical skills do you use in these projects?
Yeah, that's a good question. I would say that basically, as I described above, the instruments are mostly a combination of cameras and of spectrometers. So I think knowing something about the optics of how cameras work and also spectroscopy and, what does carbon dioxide spectra look like? What does a basalt spectra look like? What does pyroxene look like? That stuff is really helpful for the data that comes back. I would also say a lot of the images that we get back are very raw and need a lot of processing. And so understanding, how to code in Python and image process and work with image arrays and all of that is something that I use on a daily basis. Other than that, a surprising amount of Mars is knowing about geology, which I was really new to, and I think was not very clear to me when I was studying aerospace engineering, but I'm on my way to learning about it now. But yeah, the rocks are really important, especially because Mars has a surprising amount of old rocks that are almost more than 3.5 billion years old, whereas on Earth, these processes are, constantly resurfacing what's going on. So we don't actually get to preserve a lot of rock history. So understanding what really primitive life signatures look like, what do lipid molecules look like when they're preserved? How does protein actually get synthesized? These are the sort of questions that are helpful to probing, I think.
That is really interesting. Ramitu, we have again. So Ramitu, please unmute yourself and ask the question.
Thank you so much. Miss, another question I wanted to ask is now, seeing how we talked about the evolution of life on Earth and where we saw the geological changes which were occurring in the planet Mars compared to the evolution of life on Earth. So can we use the planet Mars as a model to see what the adverse effects of a solar storm what the effects of a solar storm would do to Earth? Because we could clearly assume that the atmosphere was blown away by a very, very strong solar storm, and then that led to and then in Earth we have the Van Allen radiation belts, and so to compare all those effects of the solar storm and high-speed solar particles, is it possible to use Mars as a model for that?
And you're absolutely spot on. You should come be a graduate student here. Yeah, that's exactly what a lot of people work on. Mars is a great model for, we don't really understand why it lost so much of its atmosphere so early on. We think it has to do something with the magnetic field sort of stopping, but then we don't know why the magnetic field stopped all of a sudden. So these are all really helpful analogs to see how it could go badly, in a sense. You're spot on about that.
Thank you so much, Miss.
Okay, so moving back onto the chat box, we got another question. Where do we find more information about rovers and their operations? Where can we find?
That's tricky. So there's not a lot. You're totally right. And that's for a reason. JPL is protective of rover operations and sort of the information that gets circulated. I had to have a background check. I had to get this talk cleared. So there's a lot of protocols in place. But really, I would suggest, if you're curious, you should sort of scour the websites of the Perseverance Rover. They've got some images that come in and are posted every day. And they might explain more about operations, but not much. Yeah, there's just not out there.
Okay, Hemani, so I got one personal question, my own. You showed that that bacteria that fossilized in Mars surface and fossils that fossilized in Earth's surface. So how we distinguish between these two? I mean, the bacteria that fossilized there is more similar to that geological structures called anticlines and synclines that we see on Earth. So what are the experiments and what are the things you do to identify those structures from distinguish that the structures from whether it is a bacteria fossil or whether it is anticline or a syncline?
That's an excellent question. This is the slide you were talking about, right?
Yeah.
Okay, great. So just to be clear, the right side is not a microbial fossil from Mars. These are both examples on Earth. The day we find a microbial signature on Mars, I'm gonna have a huge party, so don't get there without me. You're totally right though. Microbial mats, stromatolites, are incredibly hard to distinguish from sort of abiotic processes, because you're right, there just looks like folded rocks. It could have happened, and in fact sometimes they're formed without bacteria on Earth. This is sort of a more tame example. Some of the stronger bacterial stromatolites, they have very interesting shapes. So they'll have like domes or spirals or sort of, things that are harder to make without life. And that's when we can be sure. But we really can't be sure if we just saw something like this from a camera on Mars, But as Woody always says, actually, our assumptions should always be that everything that we see is abiotic until we can convince ourselves there's no way, there's no other possibility other than life having to make this. And really, if you see something in an unusual shape or an unusual concentration or something that goes against the energetics of the universe, that's when you can start to think that this might be life.
Okay, thank you. You unclouded my confusion. So I think you talked about that icing moons and some things about Europa. So here's one request from our audience to you. Would you mind if you can join with us for another episode to share your experiences and share your knowledge about your studies on Europa?
Oh, wow. You guys want me back already? That's so nice. If you want to know more, I'm happy to share. I think there are a lot of better experts on Europa and icy moons. I'm just getting started, but if you definitely want to have another Q&A or just an informal chat, and we can, yeah, I'd be down. I mean, icy moons are really cool. I'm down to talk about them.
Oh, wow, that's cool. Thank you too much. So, Anipurni?
We've got another question. So,
Yeah.
you're a young contributor in this mission. So, what are your experiences and what are your advices to the youngsters who love the space about climbing the ladder?
Oh, that's a good question. Yeah, I'm definitely at the bottom of the ladder, I'll tell you that. I would say that a lot of these meetings are really intimidating. There's a lot of 50-year-old scientists who've, been studying this surface for decades and decades, and they know what they're talking about. And I would say often, it's hard to find something to even contribute to the discussion, but I think there's a lot to be learned in listening, but B, also just going after opportunities and sort of looking at where you can help. So there are different aspects to operations. One is looking at the data that comes back. One is looking at the data that we send up, but there's also, people who coordinate discussions. There's also people who plan campaigns in the rover. And there's a lot of sort of menial work in like looking at maps of Mars and seeing where the interesting rocks are. And often the scientists who are really busy and experienced don't have time to do that. So if you find something like that to make yourself useful, then, that's your way to squeal in and show off a bit.
I think it is great inspiration for our young space lovers and Mars lovers. So I got one very last question for you, Hemani. How can we get this project? I think she is asking about the raw Perseverance and things. So
sorry, your audio cut out. What was the question?
Sorry, I will again explain to you. How can we get connected with this project?
Oh, yeah, for sure. So the way it happens is that there's obviously a core team, and that's the people that were in charge of making the instruments and all of that. But there's a lot of participating scientists on the mission all around the world, French, the UK, different parts of North America, Spain, all of these places. And so if you as a student apply to a university with a professor who's a participating scientist on the mission, then through them you can become a student scientist on the mission. And so that's really the way to go about it.
I think the answer is crystal clear. Okay.
I think Ramitu is up with another question. Ramitu? Ramitu, you there?
Yes, I am. So my final question is, now since we have devices like Sherlock and Supercam, so what for biosignatures, do we search for releases of substances like methane? Because methanosites can survive without oxygen, and it has been proven that there are two or more hydrogen reservoirs in Mars, as we found out with some asteroids that that we sampled. So are there any more biosignatures we can search for, like what we can see with methanosites?
Yeah, I mean, another great question. So Curiosity actually had a gas mass spectrometer, and that essentially absorbed a bunch of the atmosphere and could make measurements about what gases we saw. And so they made a lot of methane measurements and still are. And that was what my master's was about, was looking at those methane measurements. And that's definitely a biosignature that we can look at if we have, but we don't have the resolution right now because we take these measurements, once every 3 months or something, and the rover is moving and we don't know what kind of dynamics are at place. So I would say for methane specifically, it would be really helpful to actually have stable instruments on the ground in a bunch of places to actually create a network of methane measurements. And that's something that's being proposed, but there's 100 proposals. In terms of biosignatures, this payload is a bit different. And so what Sherlock and Pixel can do is really go close up with a robotic arm at these rocks. And Sherlock in particular, the way Raman spectroscopy works is it is very sensitive to the vibrational modes of the molecules and creates Raman shifts based on that. And so that would, if we ever found like aromatic rings or PAHs or amino acids, any sort of organic molecules, Sherlock would have the best chance of detecting that. So that's the kind of biosignatures I think is this rover's aim.
Thank you so much, Miss.
Yeah, of course.
Okay, so the time, the clock is ticking, and I think time has gone fast. So I think we are coming to the end of today's session. Nipuni?
Yes, Chatrika, we had a great time today in this space talk and hope you did too. So we would like to thank our guest speaker, Ms. Hemani Kalucha, for sparing some time from her busy schedule to join us and for sharing her interesting and valuable experiences with us. Thank you very much, Hemani.
Thanks so much. I had a ton of fun talking to you. Thanks for having me.
You're very welcome. And I would like to thank Professor Budi Fisher, who is a professor in geobiology, Caltech Institute of Technology, USA. And also I'd like to thank Mr. Amilasan Basnaker, who is the founder, SED Sri Lanka. And he is the one who contacted Ms. Hemani Kalucha for today's space talk. So thank you, Mr. Amila. And also Mr. Tilan Harshana, co-founder, SED Sri Lanka, Ms. Tashmila Aralia, current chair, SED Sri Lanka, and also all the board members of the SED Sri Lanka. And beside that, I would like to thank our two hosting chapters today, University of SEDS chapter in University of Colombo and SEDS chapter in University of VOYAGE. Thank you for the amazing job done behind the camera. Last but not least, I would like to thank all of you guys who are in the audience, and you asked many questions and kept this session alive. So thank you very much for joining with us. At the very last, I would like to thank my co-host Nipuni for joining with me today in today's session. Thank you, Nipuni. So until we meet from another SEDS Space Talk, another episode of VOYAGE to expand your knowledge of the cosmic horizon, stay tuned with SED Sri Lanka. Have a very good day and stay safe, y'all.
Stay safe and thank you. Bye.